This is review video 45, what are acids and bases? We've actually learned about these before, back in Unit 4 in first semester, and back then I had told you there were three main definitions of acids and bases: Arrhenius, Bronsted-Lowry, and Lewis. And I also told you that we were really only going to care about the first two in this class, and that still holds true. So as a reminder, an Arrhenius acid is something that has a hydrogen, and it's usually listed first in the compound. So a couple of examples of Arrhenius acids would be hydrochloric acid, HCl, sulfuric acid, H2SO4, acetic acid, HC2H3O2, and all of them have hydrogen, and it is listed first in the compound. But Arrhenius acids don't just have hydrogen. Specifically, to be qualified as an acid, they have to increase the concentration of H3O plus in a solution. All right? And oftentimes when we talk about acids, H plus concentration and H3O plus concentration are going to be used mostly interchangeably, and I will show you why. So if you have an Arrhenius acid, say hydrochloric acid like this one, when you introduce it into water, what it's going to do is it's going to split up into a hydrogen ion and a chloride ion, right? But as soon as that hydrogen ion enters water, all those water molecules, remember, they're polar, so they have a partially negative end here. And that partially negative end is going to be very attracted to the hydrogen ion. And this little electron pair is essentially going to reach out and form a bond with that hydrogen, creating an H3O plus. So this entire complex here is now an H3O plus. So you can kind of see how H plus and H3O plus would immediately become interchangeable, because again, as soon as that plain hydrogen ion enters water, it immediately associates with water and creates an H3O plus. So again, if you ever see them used interchangeably, that's why. Arrhenius bases, on the other hand, usually have a hydroxide, and it's generally listed last in the compound. So again, a couple of examples: sodium hydroxide, calcium hydroxide, iron 3 hydroxide. All of them have that OH, and it is listed last. But specifically, they have to be able to increase the hydroxide concentration within a solution. And that is even easier to understand than with Arrhenius acids, because those bases, when they interact with water, are going to split up, and they're going to form a positively charged cation, whatever that is, sodium, potassium, calcium, whatever, and a negatively charged hydroxide ion. All right. Acids and bases can be qualified as either strong or weak. So a strong acid and base is going to dissociate completely in water, meaning that it's going to produce more H3O plus or more OH minus ions. And that's how we define the strength of acids and bases. If they can produce a lot of H3O plus or a lot of OH minus, then we qualify them as strong. So a couple of examples of that: hydrochloric acid is a strong acid producing a ton of H plus and by extension H3O plus, and sodium hydroxide is qualified as strong, producing a lot of OH minus when it interacts with water. But weak ones, they do not dissociate completely. So whatever compound it is isn't going to break up entirely, and by extension, it's going to produce less of the H3O plus and OH minus ions in solution. So iron 3 hydroxide is a weak base, and acetic acid is a weak acid. All right, so that's Arrhenius. Arrhenius is pretty easy. You have a hydrogen, you have hydroxide. Bronsted-Lowry acids, on the other hand, are all about how they interact with other things. So if a substance is qualified as a Bronsted-Lowry acid, it is likely to be able to donate an H plus ion somewhere else. And as a reminder, H plus ions are also known as protons. Why? Because hydrogens have one proton and one electron, and when this electron goes away, you are left with a single proton. So an H plus ion is often called a proton, and you have to understand what that means. One thing is that often Arrhenius acids are also Bronsted-Lowry acids, which makes sense because if we take HCl, for example, HCl has a hydrogen, and so it could theoretically donate that hydrogen somewhere else when it interacts with another substance. All right? Bronsted-Lowry bases, on the other hand, are the exact opposite. They are likely to accept a hydrogen ion or proton from somewhere else. But it's harder to recognize a Bronsted-Lowry base because it has space to receive a hydrogen, and there are certain tricks for doing that, which I will show you as they become relevant. But you need a reaction. You need to look at an equilibrium system to really understand what's your acid, what's your base, and what are your conjugates, which is something, again, that we did in Unit 4. So if we're looking at this reaction right here, we have NH3, or ammonia, and water are reacting to produce ammonium, NH4+, and hydroxide. So we need to pay attention to what's going on with our hydrogens. We see that over here, NH3 has 3 hydrogens, but over here, there are 4 hydrogens in that similar looking molecule. So this thing, NH3, has accepted a proton. It's accepted a hydrogen from somewhere else, making this, on the left side, the Bronsted-Lowry base. On the right side, we know that Bronsted-Lowry bases, once they accept that hydrogen, become conjugate acids. Now, the water here, we see that the water has 2 hydrogens, but on the right-hand side, this most similar molecule only has 1 hydrogen. So this water has lost a hydrogen, making it the Bronsted-Lowry acid, and on the right-hand side, after it loses that hydrogen, it becomes the conjugate base, right? This one here, we see that HCl starts out with a hydrogen, and Cl- does not have one anymore, so that HCl ends up losing or donating its hydrogen, making it a Bronsted-Lowry acid, and the ion on the other side, the conjugate base. Whereas our water, in this case, we start with 2 hydrogens, and over here we end up with 3 of them, so that water actually accepts a hydrogen, making it the base, or Bronsted-Lowry base on the left, and once it accepts that hydrogen, it becomes the conjugate acid. Now I want you to look at something really quickly. In this example up top, water was an acid, but in this example down below, water was a base. Certain molecules can act as either one. They can either act as a Bronsted-Lowry acid or they can act as a Bronsted-Lowry base, depending on the situation and the molecules that they interact with. If that is the case, we say that those molecules are amphoteric, meaning that they can act as either. Water is the most famous example of an amphoteric molecule and the only one that the AP test will want you to know. But there are other molecules that can do it. You may see examples of it from time to time, but you just need to know that water is amphoteric. One more thing to remember from way back when is that reactions are going to shift away from strong substances. So if we go back up here and we look at these 2 reactions that we already analyzed, we can predict which direction these reactions are likely to shift if we see any strong substances. So in example number 2, we see hydrochloric acid. Hydrochloric acid is a strong acid, and so this reaction is likely to favor the forward direction because reactions tend to shift away from strong things. Whereas in example number 1, we don't see any strong substances here, so it's much harder to tell with this one which direction this reaction will proceed. We would have to then look up some different constant values about each substance to do that prediction, and I will teach you how to do that again when it becomes relevant. So if you have any questions about this, please let me know.